Essentially, what we're using are interferometers. And I don't know, I guess most of you know what interferometers are or have worked with them. So you take a laser, a beam splitter, you split up the beam. If you tune the lengths equal, you get a differential port over here. You place a photodetector there. And the nice thing is if a gravitational wave comes, then depending on the polarization, etc., so one arm will shrink while the other arm will stretch, and you would see a signal at this differential port. So that is the basic story that you always hear. And I hope to convince you it's a little bit more complicated than that. But with these detectors, we managed to detect 11 events so far. So maybe after you do these lectures, you will find some more. Let's see. So the data is all public. I think that is good, and many of our methods are public. So this first event that was detected on 14th of September 2015, were two black holes, about 30 solar masses each, and at a distance more than a billion light years. So that took a long time to reach Earth. And what you see depicted in green here are these gravitational waves. So space-time is very much deformed at this event, and space is stretched by hundreds of kilometers at the location of the event. But then, so the universe is practically transparent for gravitational waves. And then on September 14th, this wave reached Earth. And then this is what happened. So you see it's stretched in one direction and compressed in the other direction. So this is the way we typically show it. It was detected by the LIGO instruments, so Louisiana and Hanford. And this is how the signal looked like. So over here, I show you the proton radius. So it's 0.87 femtometer. Before I went into gravitational waves, I was in particle physics and nuclear physics. For example, I did electron scattering to measure this proton radius. And it's kind of interesting if you look at the amplitude of this wave in terms of proton radius, it's extremely small. And the other thing is that the time that this event takes is only a fraction of a second. So you would like to do measurements with a precision of something like 10 minus 18, 10 minus 19 meters. But you want to do this on a millisecond time scale. So how does this work? So people in the past tried other ways to do that, for example, with bar detectors, using cylinders of metal and then get them excited at the resonance frequency by a gravitational wave event. And it just was not sensitive enough to do a detection. So the method right now are these interferometers that you see there. So right now what is operational are the LIGO and Virgo detectors, and there's also the GEO 600 detector, but that is getting not enough sensitivity at the moment. And what we then would like to measure is typically an effect like this. So H is what we call the strain, so that is the relative change of length induced by a gravitational wave. A typical number could be like 10 to the minus 22. And then delta L is if you look at one arm, delta L is the change of the length of an arm. And of course, since you measure differential, you have two arms, you get a factor of 2 over there. So if you look at a simple Michelson interferometer and you tune the thing in such a way that the lengths are about equal, and you can go then to the output port over here, then the electric field that will arrive here will be given by the difference of the fields from both arms, and then there will be a phase difference developed depending on the length in each arm. So this is typically what you get. This and this expression is completely equivalent. It's just writing one to the other. And then if you would like to know the power, you just square the electric field. So you take the complex conjugate and you multiply, and you get this expression over here or this one over here, again equivalent. So that is what you expect for the output power on that photodetector as function of a phase difference, and the phase difference will be induced then by, for example, a gravitational wave. So with an installation like that, Michelson, so about more than 100 years ago, did his measurements on the constancy of the speed of light, and was capable to determine the movement of a fringe by something like 1/20th of a wavelength. So the wavelength that we are using right now are on the order of a micron, so 10⁻⁶ meter. And so that means that if you can measure with this precision, you use a wavelength of half a micron, then typically delta L over L that you're sensitive to is a strain of something like 10⁻⁹, a few times 10⁻⁹. So we would like to do 10⁻22. So you need to do much better than this measurement. So if you look at the output power on that photodiode, so that's given by this expression over here, then what you could do is, in your mind, an experiment where you put one photon, you inject one photon in this interferometer over here, and then you see whether you detect it here or not. So like, are you on a bright or a dark fringe? You would like to see that difference. If you would do that on, for example, on a LIGO detector, then a crude estimate of your sensitivity between a dark and a bright fringe will be half a wavelength. Your optical length is 4 kilometers, and your sensitivity is about 10⁻⁻. So again, not good enough to just use an interferometer that way. So if you would like to go to 10⁻22, you need to do 12 orders of magnitude better. So what you could do then is, okay, and then use 10 to the 24 photons and just repeat the experiment. And repeat it every millisecond or every 10 milliseconds, because that is the precision that you would like to have. Now, if you multiply that, you know, the energy in a single photon, you need about 20 megawatts of power if you would like to do that. So that is something that is not possible right now, to inject this kind of power in the interferometer. And Virgo uses a typically injected power of 1,000,000 times less. So how is this done? Another thing that you need to do are these mirrors that you see here. Actually, all these main optical components, you cannot put them on the ground. And if I were to put a sensor on the ground and would measure the vibrations here, then typically this would move somewhere between a micron and a nanometer. Typically that would be the displacements, and you would have that everywhere on Earth. So you cannot put things just simply on the floor. And you need to create something that looks like a free-falling object. Now, free-falling objects you can do in space, for example, with the LISA interferometer in space, but it's much more difficult on Earth, so you have to hold it in some way. And typically what we do is take a mass and put it on a pendulum, and then try to mimic a free-falling test mass. So the mirrors we call test masses, because they're used to probe the change in length. Now, if you look at the mass here hanging on a suspension, and this is connected to the ground, because that is the structure where you suspend your mass, and you would move that, then part of that movement you would see back in the movement of this mass. And typically, imagine that you have this mirror here hanging on wires, then it will swing at a resonance frequency. If I move it slower than the resonance frequency, lower frequencies, it will just follow. The transfer function will be 1. But if I move it much faster than the resonance frequency, then that will not be seen by this mass here. That will be damped. And typically what you do when you without any doubt have done this before, is write down the equation of motion. So you have the inertial term over here, and the mass times the acceleration, the damping term, and then the restoring force here in the pendulum due to gravity. You can go to the frequency domain, and you can find the solution over here, and then you define the resonance frequency in this way, and the Q factor, the quality factor of that oscillator, and that is related to the damping of that oscillator. So if you plot that, then that transmissibility, the transfer function between moving at the top and how quiet the mass is shown over here as function of frequency. So here you see the resonance frequency, and you can calculate what the displacement is here at the resonance frequency. And you see it's amplified by the Q factor. So there you make things worse. But at low frequency, essentially, the mirror is just following what is happening on top, as I told you. But at high frequency, you see that the motion of the mirror is much less than the motion of the top. So there is a suppression of this movement. And that goes with 1 over the frequency squared. So here you see the damping of these frequencies. So at high frequencies, essentially only this term is dominant. And this term is the term that is going with the inertial mass. So it's the term that is just only dependent on the mass. So in that sense, this mirror is like a free-falling test mass. So at these high frequencies, you don't see anything else anymore. It's like the whole suspension system is not there. So that is the idea behind suspending mirrors in this way. Another thing that I would like to go through very fast, but because I assume that you have seen it, is that the gravitational waves essentially space-time, and you can write your general metric like Minkowski plus this small deviation here in the metric that we call then this due to gravitational waves. And now assume that when you have the two mirrors, that the gravitational wave effect is a constant effect there. So it's not frequency dependent. Then you can write on the typical interval over here. You can rewrite that and look at the time that it takes to propagate between the mirrors, and then integrate this expression over here. And essentially what you see is that the time it takes, and essentially the time that the wavefront is taking through the arms, is proportional to the length and the size of the amplitude of the gravitational wave. And what we are typically doing here is we're working in a transverse traceless gauge. That means that we have chosen the coordinate so special that the gravitational wave is going in the z direction, that the deformations of space-time, the polarizations, are orthogonal to that, transverse to that. And traceless means that if you shrink something, for example, in the x direction, then automatically you stretch it in the y direction. So that is a very special frame. The other thing that we have done is that we have chosen the coordinate such that the beam splitter is always at position 0 and the mirror is always at position L. So it's like coordinates that are moving with these mirrors. So in that thinking, that coordinate distance is not changing. What is changing is this metric. And the real physical distances are the product of the two. Okay, so from that, then in this picture you can derive that the phase difference that you can detect with your gravitational wave is given by this expression. So it's proportional to this h, the amplitude of the gravitational wave. It will become bigger if you have a longer interferometer and if you have shorter wavelength. So that was for a constant gravitational wave amplitude. But now imagine that you have something that is time dependent over here, or frequency dependent. So, and then you would have to do it a bit more complicated. The expression would look like this. And essentially what you see here is that if you would have a Michelson interferometer with an arm of 4 kilometers, you would get a certain sensitivity that is shown over here. And if you make it longer, for example, 75 kilometers, then your sensitivity would improve. But you would also start averaging. At some point you start losing sensitivity, because if you make it very long, then you store the light so long in your cavity that the gravitational wave is changing during the storage time, and you are averaging the effect away. So that's what you see here. So that point is called the cavity pole. So now we need a few tricks, because I just showed you the sensitivity, but also I told you we need about 20 megawatts to do the measurement, so that is not going to work. So one of the things, and that is an idea of Ron Drever, is to just not use one mirror, but to make a cavity of two mirrors, Fabry-Perot cavity. And if you look at this, then power will start building up in that cavity, and essentially what you get is a behavior that looks like this. So the cavity, the quality of the cavity, you can express in the finesse, and that finesse is given by reflection and transmission coefficients of the cavity. You just can calculate it. And if you know the finesse, you know also the effective number of bounces in a cavity. So what this does artificially, by making that cavity, you get, for example, for Virgo, if you put in the numbers, you get a finesse of 440 right now, and about 280 bounces. That means that instead of 3 kilometers, our interferometer is now 840 kilometers effectively, because of all these bounces. So that is the trick of using the Fabry-Perot cavities. And in the calculation of this 12 orders of magnitude, of course it helps a lot if the effective length is longer. This goes in quadratically in reducing the power that you would need. So here you see again a simple Michelson interferometer, the sensitivity of that. And now you make Fabry-Perot cavities like in Virgo and in LIGO, and you see that the sensitivity increases significantly by this factor 280. So still, in order to do this, and if you would like to run like that, you still would need kilowatts of power injected into the interferometer. So also that is not good enough. And there is a second idea that came from Ron Drever, is that why don't we do power recycling? Because we tune the interferometer to a dark fringe. There is where we are most sensitive, close to a dark fringe. That means that all the light has to go back in the direction of the laser. So why don't we place a mirror here and make an additional cavity? So that is what is done. So when an additional mirror is placed, and you make a free mirror cavity over here. So these Fabry-Perot, you can look at that like an effective mirror, or this point over here. And in that way, you start recycling the light that otherwise would be lost, and you coherently add new laser light to that. And that the power effectively builds up by another factor 80 to do that. So that is power recycling, and both LIGO and Virgo are using that in order to be able to work with tens of watts of laser power and effectively create kilowatts of power. There is another idea from Brian Mears that is called signal recycling. And the idea behind that is that normally when you're operating, you have no gravitational waves, then there will be no field over here at this port where you have the photodetector. So what you could do is place a mirror there, and again make a free mirror cavity, that if a gravitational wave is detected and a field is coming in this direction, you can reflect it back and start coherently building up with the new gravitational wave signal that is coming in. So that is called signal recycling. At this moment, this is installed in LIGO, not in Virgo. And we pay quite a price for that, as I will show you in a second. So this is something that we will do immediately after we completed the current run. So in all, what LIGO and Virgo are dual recycled Fabry-Perot Michelson interferometers. So there is a recycling of power and there is recycling of signal. And then you have to get all of this locked. So I would like to show you this little movie over here. So here you see Virgo. This is one of the 3 kilometer long arms. And here you see, this is part of the vacuum system. This is the detector table, where at the end you have the sensors, just photodetectors, that measure the signal of gravitational waves. electronics. This video tells you a bit about log acquisition. So that is, how do you tune all the mirrors in such a way that the thing operates in a stable manner. There should be some sound, but I probably can tell you the story. So there is a laser where a beam splitter, two mirrors at the end. And then this is where the photo detector is. And you tune it, and typically in a way that you're almost at the dark fringe. Not completely at the dark fringe, but very close to it. So if you would do it this way, as I told you, you would need like 20 megawatts of power injected in the interferometer in order to operate. So if a gravitational wave comes, you get stretching of one arm, the other one gets shorter, and then you see a signal on this photodiode. And essentially that is the signal that we show you also in the papers. Here we start putting in additional mirrors, so input test masses and end test masses, and now tuning the interferometer in such a way first that these cavities are on resonance. So that is the first step of locking the interferometer. Now very soon there should appear a power recycling mirror. Yeah, so now you see that you lose all the power going back to the laser. So again, you place this mirror here in order to build up additional power in the interferometer. And then what you do is you can move this beam splitter in such a way that you lock the two arms and get everything operational. I think that is what you're going to see right now. So you see the power going between 0 and its maximum. And the first thing that we do is that we lock on what we call half fringe. So we go to operate on half the power, somewhere over here. So that is tuning is done by moving the beam splitter. So that is happening right now. So in this, what we are not doing right now is power recycling. So this was a little bit off. We tuned that maybe 60 microradian off. And then we also tune this such that the power is reflected and the length is also so that it's on resonance. After then power builds up, then we start moving again the beam splitter in a way that this port is becoming dark. So when you are half fringe, half of your power is just lost out of the dark port in the direction of this photodiode. While if you go to dark fringe over here, the power stays in the interferometer and you start building up power everywhere. So this is just a small concept of what we are doing. In reality, this is way more complicated. And the other thing that you have is that I already said there is seismic noise. Typically, the seismic noise on these components, on all the components, we have to suppress by up to 15 orders of magnitude. Otherwise, we cannot do measurements. Then there is gas. So when the system has to operate in vacuum, otherwise, and even at the pressures of something like 10⁻⁸ millibar, the residual gas, the fluctuations of that, gives you an effective index of refraction that is enough to limit the experiment. So also this, and these are the, for example, Virgo is right now the biggest volume vacuum system in Europe. It's all ultra-high vacuum. Then there is laser noise, so the laser has to be stabilized in frequency and in power. In power, typically it's stabilized to something like 1 part in 10 to the 8. But frequency is your measuring stick, so that has to be stabilized to the same precision as you want to do your measurement. Then there is shot noise. So you need a certain amount of power in the interferometer, And there's radiation pressure, and you see that they act in opposite. You need lots of power in order to do good measurements, especially at high frequency. But if you have lots of power, you start pushing on your mirrors, and that is again limiting your sensitivity. And there is thermal noise, so that is what thermodynamics tells you. Everything has a thermal noise. You could operate an interferometer cryogenically. That is what is being implemented right now in Japan. And they should become operational later this year. And thermal refractive noise, that means that also if your temperature changes, your index of refraction is changing. So these are a few of the noise sources. We talk about fundamental noise sources. These are just limited by physics, like Heisenberg uncertainty principle. You cannot do much about that. And technical noises, which you, for example, seismic, where you can do something about, go to a more quiet site. So looking at these fundamental limits, one is shot noise, and essentially the quantum nature of light, so that it's made out of photons. And the statistics is governed by Poisson statistics, so that number, the rate of photons hitting your photodetector for large numbers goes with, the uncertainty goes with the square root. So typically you get then that you have a shot noise limit, which you can reduce by increasing the laser power. Now, if you do that, then at the same time you get radiation pressure noise, because you have a static pressure, you have these cavities, and the photons are going in the cavities like that, so they're really pushing the mirrors. So this is the static force. But there again, then there is this uncertainty on this number, which goes with the square root. And so that then translates into radiation pressure noise, where now the power is up. So it's so you can make a trade-off between one or the two. So if you go to a certain frequency, then at a certain frequency there is an optimum power that minimizes the sum of radiation pressure and shot noise. So that's of course a bit difficult in reality, because you put one power in your interferometer. Then the working point. So if you look at this curve over here, where you have the power and the phase, then you would think, if I am half fringe over here, then this derivative is steepest, and here I would have the best sensitivity to gravitational waves. So indeed, that part is true. The only problem is that here you're operating with half the power at the dark port, and if you look at your power fluctuations of your laser, they are quite high. So if you want to optimize the signal over noise ratio and not your sensitivity, then you will see that it's better to operate very close to the dark fringe. And that is typically what we do. You could not work half fringe. You would not have the precision. Then there is seismic noise. I already told you that the typical spectrum, for example, at our site, are displacements above, say, 10 hertz, which in the order of 10⁻⁷ meters, and they drop by 1 over the frequency squared in displacement. It's a difference between day and night. In day, people are working and making more noise, and also whether there is good weather or bad weather. So hopefully our sensitivity at Virgo will improve once we go into the summer. Yeah, you laugh, but it's really true, because there was lots of wind, lots of sea activity, which makes that in order for us to keep locking the interferometer, we have to use more feedback force, and that introduces more noise. So again, how do you get rid of this seismic noise? I already told you that if you hang your mirror on a pendulum, then you have this resonance frequency, and above that frequency, the displacements of the mirror are damped by 1 over the frequency squared. And so this is nice, but we want to start operating from 10 hertz on. And you get a damping right now of 2 orders of magnitude, so that is not good enough. So what we do there is we cascade many of these pendula. So that's something that you can do. So we do typically like 7 in our system at Virgo. So these are mechanical systems, and very, very effective. So you get now a cutoff that goes with 1 to the power of minus 2n. So where n is the number of stages that you have in your pendulum. And so here you see already you go to 10 orders of magnitude and below 10 hertz. And then you hang your mirror at the bottom of this. And again, you can see that if you do that, whether it's a free pendulum or if you hang it on the super attenuator above a few hertz, it has exactly the same behavior. So this would be to isolate only in this horizontal motion, but we need to do this vibration isolation in all 6 degrees of freedom. So we need to do it in x, y, and z, and also in all the angles. And life is tough, because at these distances of 3 or 4 kilometers, you need the mirrors hanging like this in order for the beam to be reflected. But of course, they would like to hang towards the center of the Earth. And that already gives a coupling from horizontal to vertical. And then there are imperfections in how good you can put mechanics together, and typically you get couplings in the order of up to 1%. So you need also isolation not only in these horizontal degrees of freedom, but also in the vertical degrees of freedom and in the angles. So we use torsions of wires to do that. We use in Virgo something that are called anti-springs, magnetic anti-springs, for vertical isolation. And essentially what you do is you take 2 magnets with North Pole and South Pole, and you put them together. If you do that, then it's a very unstable system that would like to shoot out in every direction. So these kind of system, and then with flexible blades in the vertical direction, are giving our vertical isolation, also at a very high level of isolation. Then there is Brownian motion. So the mirrors typically have quality factors when we suspend them in the order of 10 to the 8. So if you hit them, they will keep ringing for a very long time. And if you make this quality factor very high, then of course at the resonance it will be terrible, you cannot measure. But around the resonance here, you see that your sensitivity improves. That is something it's called the fluctuation dissipation theorem. In order to achieve that, our mirrors, like 42 kilograms of mirrors, are hanging from quartz fibers. And it's like a welding of glass on glass to do that, and that has this high quality factor. We were troubled in the past with breaking glass and things like that. Now the isolation is so good that if the optical beam is hitting the mirrors, and it can excite mechanical resonances in the mirrors, and they start ringing in there. And if you're exactly on resonance, all your power will go into that mode, and your interferometer will become unstable. That's what we call parametric instabilities. It's like if you have somebody on a swing, and just at the right point, you keep giving a little bit of energy, at the end it will keep up swinging. As long as the Q factor is high, and the Q factors here are 10 to the 8. So I just tried to give you an impression that if you look at the sensitivity curve of our experiment, which looks typically like that here we're completely limited by shot noise. Here we are limited by the radiation pressure. In the center we are limited by thermal noise in the coatings. And it's a very complicated story. We need to understand all of these noise sources in detail. Over the years, this is the progress that was made in getting the sensitivity to a design value. And we're right now trying to reach this curve over here. And we are at about halfway at the moment. And for 2017, the idea was that we would be somewhere between 20 and 60 megaparsec. So what we had on average in the run in 2017 was 26 megaparsec. Now, for joining the second run, which now started in April, was supposed to start earlier, we were shooting at 60 megaparsec. We didn't achieve that. We are at 50 at the moment. We still are working to improve that. Nevertheless, we joined. So this happened on April 1. Many people were relieved about working for 1.5 years only on looking at noise and trying to decrease noise and improve the instruments. Same was happening with LIGO. And at the end, this was achieved. So you see this band, which was our goal. This in purple is what we had in the previous run. And now in blue, you see we achieved here what we wanted to do. We achieved it at higher frequencies, so the shot noise is fine, but we're lacking something over here. And we brought it by 50 hertz. Something in the electronics is picking up 50 hertz. As soon as we solve one of these two things, I think we are fine, but we are looking at it. This, if you compare the LIGO sensitivity with the Virgo sensitivity, then you see only at the lowest frequencies we are about equal. And here the sensitivity difference is quite large. The reason for that difference is that Virgo does not have signal recycling, and LIGO has. So you see immediately that makes a big impact on your sensitivity. This is the detector Geo in Germany, which has only 600 meter arms. You see, if you do that, it makes it impossible to come close. They get somewhat close here at highest frequencies. The good news about Virgo, it's very stable. So it's running at lower sensitivity, but it's quite stable right now. The other thing is, if you look at the interferometers together, then what is indicated in green, so green is good, is that we have about 42% of the time triple coincidences with these detectors. So that is nice. Another thing that we implemented is squeezing. So squeezing is you're essentially manipulating the vacuum a bit, injecting noise into this dartboard with a very specific type of noise. And that makes that your sensitivity, by just injecting a few milliwatts of that squeeze light, is improving here. So with this 3 dB, it is essentially doubling the laser power effectively by just using squeeze light. The idea behind that is that in squeeze light, so I showed you the shot noise and the Poisson statistics and things like that, but with squeeze light you are correlating the photons. And that improvement that you get over here, you see that actually on this side it becomes worse. So here you see that you're losing because of the radiation pressure effect. So what we would like to do in the future is make the squeezing in such a way that we not only gain here, but also here. And that is called frequency-dependent squeezing. So how does the future look like? So right now, these 3 detectors are operational. Later this year, Kagera will join the network. They're working very hard. They have a cryogenic interferometer, extremely ambitious, lots of work. But we look forward for them to join. And there is the detector in India. In India, the construction started in January this year. So the anticipation is that by 2025, also that detector will join. And then the advantage of having these detectors is that we have very, very good sky pointing. All of that is not enough. What we also want to do is within the constraints of the sites that we have, both for LIGO and Virgo, we would like to improve these detectors as much as we can. And so there are upgrade programs approved, both at LIGO and at Virgo, that are called A+ and Advanced Virgo Plus. And the idea is essentially to double the sensitivity again, and do that by frequency-dependent squeezing, working on the size of the mirrors, etc. I will skip the technical details because the chairman is getting a bit impatient. So it's a big activity, and to, for example, try to make these mirrors now from 42 kilograms up to more than 100 kilograms. The idea behind that is that if you make the mirrors heavier, then of course things like radiation pressure, it will be much more difficult to push 100 kilograms than 40 kilograms. And the other thing is that if you make the beam sizes bigger, you start averaging more over your thermal noise, and you get more precision also from that aspect. But all of that has to be prototyped. Then there is the final thing for, I guess, this century, and that is to go to third generation. So gravitational waves, I think 20 years from now, will be just a regular component of astronomy, just like gamma rays or any other field. But you would like to observe the entire universe. So with LIGO and Virgo, what we can do is detect events in the local universe, but you would like to go into observing the entire universe. So with Hubble, for example, we were able to make images up to something like a redshift of 12. I think that was the maximum. With James Webb, maybe up to 20. So we would like to build devices for gravitational waves. So in Europe, that's called Einstein Telescope. In the US, it's called Cosmic Explorer. But these will be instruments that will again be an order of magnitude more sensitive. And if you make it an order of magnitude more sensitive, then typically the event rate goes with the third power. Not completely, but typically. So this is what you could cover. So with Einstein Telescope and Cosmic Explorer, you could reach redshifts up to something like 100. Now this is incredible if you look at that. I don't know whether you come from astronomy, but this really should impress you, because it will be very, very hard to put anything that would work electromagnetic and get these kind of reaches. The reason is simple, is we measure an amplitude and not an intensity. I think that is the main thing behind. And this is the range in black hole masses that we can cover. So I will skip all the science and conclude here. Okay, thank you.